Okay, but let's go ahead and get started. So welcome back to MAT1841 as we go on our whirlwind tour of some basic algebraic topology. So what did we do last time? Well, we defined Cech complexes. So a simplicial complex that arises from this ball covering of your data set. We also proved Helly's theorem, which was the thing we proved at the very end, where we were basically saying if you have what was the statement again? If you have convex closed sets, a finite collection of them. If you have a finite collection of them, then if D plus one of them have a non-empty intersection, then that means all of them have a non-empty intersection, assuming your D is the dimensionality of your Euclidean space. So that's what we ended doing last time. And now let's go back to the Cech complex and talk about how to actually compute it, right? So we have this complex, we've defined it, but since this is a more applied class, we have to actually compute it if we're going to do anything useful with it, right? But now that we've proved Helly's theorem, well, then we can say something additional about Cech complexes. But let's first note that, so we're going back to computing Cech complexes. Note that a set of balls of equal radius, has a non-empty intersection, if and only if all of their centers lie in a ball of the same radius. In a ball of the same radius. Right, and that should be pretty obvious. In order for them to all have a non-empty intersection, there must be some common point, and that point has to be less than or equal to the distance r from all the centers of the balls to begin with. And so you can also think of all their centers as lying in some ball. And this, of course, implies, so if you write this a little bit more formally, y belongs to all balls if and only if the distance between x and y is less than or equal to r for all centers. All centers x in X, where X is our original collection. And so we get a nice corollary to Helly's theorem. This is also known as Jungs Theorem, which is that if we let, we have some finite collection of points in Rd, then we note that every D plus one points in X are contained in a common ball of radius r, if and only if all points in X are, right? So this is just a straightforward application of Helly's theorem, where instead of using arbitrary convex closed sets, we're using, well, convex closed balls of the same radius. Okay, so now let's think about sigma contained in X. When we know that sigma is in the Cech complex. So here sigma is so here I am identifying together a subset of my points in X with the simplex that would appear in the Cech complex containing those as vertices. Okay, does that make sense?
Can you repeat that? Sorry.
Yeah, so remember that a Cech complex is the cover that we're using for Cech complex is for each of your points in X, you're drawing a ball around it, right? But then when you're looking at the nerve of that, which is your Cech complex, you have a simplex precisely if those balls intersect mutually, right? But because of the sets that we're using for the cover are just balls around each of our points, we can identify those balls with the points themselves, right? And so here what I'm saying is I'm letting sigma be some subset of those points. And you can also think of some subset of those points as some potential simplex in your Cech complex. So if you have the points A, B, C, well, then you might be like, well, does the triangle ABC, the filled in triangle ABC exist in your Cech complex? And that's basically what we're saying. So if sigma is some subset of our points, then we're saying that the balls containing those all have a mutual intersection if it's in the Cech complex. And so I'm using sigma to refer to both the subset as well as the simplex in the Cech complex. So if we have some sigma, which is a subset of X, then sigma is a simplex in the Cech complex of X and R. If sigma is contained, and here I'm using sigma again as a set of points, not as a simplex now. So going back to using sigma as a set of points. If sigma as a set of points is contained in the ball of radius R around some y for, well, some y in R to the D. Okay, so this is just putting together the different things we just said about, oh, well, if it's in the Cech complex, and that must mean that there's some mutual intersection of the balls surrounding those points. And if there's some mutual intersection of those balls surrounding those points, then the points themselves, which are the centers of those balls, must be contained in some other ball around some other point. Okay. Well, now let's define something. We're going to call it a mini ball around sigma. And this is going to be the smallest closed ball. Smallest closed ball containing sigma. Okay, and this is unique, of course, because like if you have some collection of points, there's always some smallest ball you can draw around all those points. And the radius of mini ball of R, of sigma, is if this radius is less than R, then that implies that sigma is in the Cech complex. Right? Because if the smallest ball containing it has a radius that's bigger than R, then that means that, well, you don't have a ball of radius R that contains all those points. So if we want to ask ourselves, is a particular simplex in the Cech complex, all we have to do is ask, what is the smallest size of a ball that contains those points as points in RD? Maybe it is less than or equal to. It doesn't really matter. Wait, so if it's less than R, yeah, sure. Well, less than or equal to. Yep. Okay. So now what we need to do is now we need to figure out, now we need some way of computing, computing the smallest ball that contains a bunch of points in Euclidean space. But now all of a sudden we've taken this problem of figuring out what a Cech complex is, and we turned it into a problem of geometry. So all we have to do is we need to do some computational geometry and figure out what the size of the smallest ball containing a collection of points is. So let's discuss that a little bit. And one thing to note first, and this will be important, is that a mini ball is determined entirely by boundary points. Determined by boundary points. So we can remove any interior points. Remove interior points. Right? I mean, like if you have a ball and you have a point on the interior of some set, you don't need that point to define the mini ball. And that brings us to an algorithm. So this algorithm will return the mini ball. So we're going to define this algorithm recursively and then look at its runtime. So we're going to return the mini ball with some set in the interior, with tau in the interior, and nu on the boundary. Okay, so now this function is going to return something slightly different than our original function, right? Originally, we want just like some way of computing the mini ball of some set of points, right? And now what we're saying is, well, let's suppose that we define some algorithm that we're going to define this algorithm recursively that does it based on some collection of interior and exterior points. And obviously, you don't need to worry about the interior points, so you can just discard them. But what we're going to basically do is we're going to use this algorithm to constantly move points from what we consider the interior, from what we consider the boundary to the interior, so we don't have to worry about them. And then once you have a small enough set of points, then it'll be easy to directly compute the ball. So let's see, we're going to define mini ball of tau and nu. So the first step is if tau is the empty set, then we can compute the mini ball B of nu directly. Okay, so if you know that all these points are already on the boundary, well, then there are a bunch of ways that you can, like, those define some circle. So if you know the points on the edge of the circle, well, that defines some circle, like that. And you can do this with some sort of least squares, whatever, because you know the distance. You don't even need to do that. You just need to, if all your points you know are on the boundary, then all you have to do is you need to look for a point that is in the intersection of all the circles. That is exactly that distance away from everything. You could do it a couple different ways. One is you could just like draw out all the bisection planes and then find that intersection. Another way is you could do some sort of least squares thing, and that will quickly get the mini ball as well. So life is easy if all your points defining your mini ball you know to be on the boundary. But now we don't know that we don't know which points are on the boundary and which points are on the interior a priori. So we need to figure out some way of taking points and deciding whether they're on the boundary or if they're on the interior, right? So if everything is already on the interior, if everything's already on the boundary, then we're done. If everything's not on the boundary, what we're going to do is we're going to iteratively remove things. So else we're going to choose a random element. Here, the randomness is actually important. U in tau. Okay, we're going to choose a random element, and then we're going to say B is equal to the mini ball of tau minus U. So we're going to subtract it away from the interior. So remove U from interior. So now I should be a little bit cautious. Like, this isn't the actual interior. This is what we consider to be the interior. So this is what the things we know to be. When we say the boundary, we mean the things we know to be on the boundary. So remove U from the set of points that are putatively in the interior. And then you ask the question. The question is U actually in the interior? So if U is not in B, so we just defined B as the mini ball from this thing minus this point. So, but if it's not in B, well, then that means that it wasn't in the interior, it was actually a boundary point. And if it was actually a boundary point, then we need to move U over to the boundary. So then B is equal to the mini ball tau minus U nu union U. Okay, so we've removed the U from the interior, and now we're put U in boundary if necessary. Boundary if necessary. Okay, so basically what we're doing is you can think of this as we're starting off with all the points we don't know that they're on the boundary. We test each of them iteratively, and then we're like, if you remove that point, do you get the correct thing? If so, then you put it on the boundary. If so, then you just discard it entirely since it doesn't matter. If not, then you put it on the boundary. And eventually you'll like fill up the boundary, right? And then at the end of this algorithm, so this is a recursive algorithm, you return B. And now this is recursive because we're calling the algorithm itself on some smaller set of inputs, right? Then after we do all this, then the mini ball of sigma and the empty set is equal to the mini ball of sigma. Okay. How long does this algorithm take? So tau starts off as being all the things in sigma. And then you either in each step you either subtract it out or you move it over into the boundary. And let's see, did I define the number of things right now? Let's say we have n points. Let's say the size of sigma is n. So how long does this take? Yeah, so initially tau is basically all things we don't know that they're on the boundary or not. And so tau is the set of things we're working with, and then we take things out from tau, and then we either put it into the boundary new, or we just discard it entirely.
What is new initially?
Nothing. So no, initially we don't know that. So like this is like I said, like describing it as the interior and the boundary isn't quite right. Tau is all the things where we don't know where they go, and the new is all the things that we know it has to be on the boundary. And so the algorithm runs by moving things over from tau over to nu, or just throwing them out entirely.
In order for it to check like one point, it then has to recursively check all the other ones, correct?
Yes.
Factorial?
So not quite, although you're on sort of the right idea. So we need, so let me write it out. So each iteration reduces tau by 1, right? So each iteration reduces tau by 1 at the cost of possibly 2 recursive calls. Right? So if you have, so like once you get to the point where tau is an empty set, let's call that operation 0 time, because it doesn't, like we're measuring this in terms of how many times you're calling this function, this recursive function. And so this means that if things are bad, this takes possibly exponential time, 2 to the n time. Why? Because we know that takes n steps, right? But each time you run the step, you might have to call mini ball twice, because you might have to call it there. Well, you always have to call it there, and you might have to call it there. So I guess it's less like yeah. So you can think of it as a binary tree. But so if you actually had to take all these different paths and call mini ball this many times, that would be really bad, and like this algorithm would not terminate in a reasonable amount of time. Yeah. What's our saving grace here?
Oh, most points are located on the boundary.
No, most points are not located on the boundary. Most points are in the interior. Yeah, so right, like if you have a bunch of points n in some space, and you're thinking about like the convex hull of a bunch, I mean, this isn't quite a convex hull, but let's think about it as that, because that's a little bit easier to think of. So if you take the convex hull of a bunch of points, just arbitrarily scattered around, most of them will be in the interior. They won't be like the defining points. And the same is true for this big ball. Like most points are not on the edge of a ball. Like if you think about this probabilistically, most points are not going to be exactly on the edge. In fact, it turns out that there is a limit on the number of points that can be on the edge. Like it's like the ball is defined entirely by d+1 points, right? And so most points will probably not be on the edge, which means that most of the time you don't need to do the second call, because most of the time it won't be in B. Or sorry, most of the time it will be in B. So unless we can control the conditional if U is not in B. Because if you think about it, if you get really, really lucky, if every time you choose a point, if you like you throw out some point that's not in there, then well, that's actually in the interior, then you don't have to do anything. But of course, you can't be that lucky, because you need to have a certain number of points to define the boundary. So the question is, how often does this happen? And we can control this. So let's let Tj of n be the expected computational complexity. Computational complexity with n points in tau. Okay. So basically, we're asking if you have if you still have a bunch of points in tau that you haven't moved over into one side or the other, or like you haven't moved into the boundary or thrown away, what is the expected computational complexity? And let's let be with n points, and let G be equal to d+1 minus nu, possibly open positions on the boundary. Possibly open positions on the boundary. Right, because if you have d+1 points, that would completely define your boundary already. And so there are only so many spots left for the point that you're choosing of whether it's in your boundary or not. Let's see. And your guess about factorial actually does come into play here. So we'll see that in a moment. So what are these values? Well, Tj of 0 is equal to 0. And this is because you have 0 calls. Like if everything's already on the boundary, then you can just compute it directly. So by this, I mean 0 calls to mini ball, the recursive function. Now, if n is greater than 0, the probability that U is not in B is exactly the probability that U needs to be a boundary element. right? And what is that? We have, yeah, so this is less than or equal to j over n. Yeah, right? So this is less than or equal to j over n because you have j different positions and you're randomly picking stuff. And so clearly you're going to have something that's, you're going to pick a boundary element, probably j over n. Actually, I think this might be equal, but like it's certainly less than or equal to. Plus tjn is less than or equal to tj n minus 1 plus 1 plus j over n times tj minus 1 n minus 1. Why is that? Because this here is mini ball of tau minus u nu. This here is checking if u is in B. And this here is the mini ball of tau minus u and nu union u. Okay, so but if this is the case, then let's do an easy one. So what's t0 n going to be equal to? This is less than or equal to t0 n minus 1 plus 1, right? And this is if you have no spaces left on the boundary. Because if you have no spaces left on the boundary, well, then at each step, you're just going to discard whatever element you picked. And you could skip all that step, but like at most, this means that t0 of n, what's the runtime of this going to be? Yeah, it's just going to be less than or equal to n. What about t1 of n? This is going to be less than or equal to t1 of n minus 1 plus 1 plus 1 over n times t naught of n minus 1. Well, we can plug in t0 of n, which is less than or equal to n. So this entire thing is less than or equal to t1 of n minus 1 plus 2, right? And so this implies that t1 of n is less than or equal to 2n. And t2 of n, well, this is going to be less than or equal to t2 of n minus 1 plus 1 plus 2 over n times t1 of n minus 1. But this, of course, is just 2n. And so then this is less than or equal to t2 n minus 1 plus 5, which implies that t2 is less than of n is less than or equal to 5n. Now 5 is less than 6. So I'm just going to say this is less than or equal to 6n. When 6 is less than or equal to 3 factorial. I mean, it's just equal, but I'm using less than or equal to everywhere here. And you'll notice that what's happening here is whenever I take the next thing, so it's t3n, that's just equal to t3n minus 1 plus 1 plus 3 times 3 factorial. But 1 plus 3 times 3 factorial is, of course, less than 4 factorial. So this is less than or equal to t3 of n, which is less than or t3 of n is less than or equal to 4 factorial times n, and so on. And so if you keep on going, this means that tj of n is less than or equal to j plus 1 factorial times n. Okay, but notice that j is less than or equal to d plus 1 because we have at most d plus 1 boundary points. At most d plus 1 boundary points. So for constant dimension, the algorithm takes O of n time to compute a mini ball. Okay, this still isn't great because, of course, it has a factorial term in terms of the dimension. But in terms of the number of points, this means that you can compute the smallest ball that contains all those points relatively easily. Any questions about all that? So basically what we're saying is that you can actually compute the Cech complex, and all you have to do is you need to check if each of these simplices is present. This is also not so great, though, because it turns out that in order to actually compute the Cech complex, you need to check all these subcollections, right? So then you're checking all of these if an exponential number of simplices are present. And so in practice, this isn't actually what people do. So this is computable, but this is still a little bit unwieldy. So in practice, people don't often use the Cech complex. Instead, they use something called the Vietoris-Rips complex. So no, it's not worst case. But like you do have some control over, yeah, but you have control over the randomness because you get to pick a point randomly. But like the big problem with this is that you are checking all subcollections of points. So you have to ask, oh, is the simplex 1, 2, 3, 4, 5 here? Is the simplex 1, 2, 3, 4, 5, 6 here? Is the simplex 2, 3, 4, 5, 6 here? And so on. And so like actually computing the Cech complex this way is doable, but like expensive. So often people use another complex that is, you can sort of think of it as the approximation of the Cech complex where you only check pairs. And if all the pairs are present, you're like, okay, well, the entire simplex is probably present. So let's define that. So let X be in R to the D, a finite set of points. Then the Vietoris-Rips complex, Vietoris-Rips complex of X and R is defined by, say, VR of X and R is equal to a set of sigma contained in X such that VR of Xi intersect VR of Xj is non-empty for all Xi, Xj in sigma. That is to say, the Vietoris-Rips complex of XR contains all subsets of X with diameter no greater than 2R. And basically what we're doing here is in the Cech complex, if you wanted to tell if this was present, you'd have to check if there's some mutual intersection of all three of these, right? Whereas in the Vietoris-Rips complex, you're just checking each of these edges. And then you're like, oh, well, if I have all the edges, well, let's just go ahead and say that simplex is present. Okay, so well, like instead of actually explicitly checking all of them. And so this turns the problem down from checking all pairs of edges. And checking all pairs of edges is, well, that's just quadratic, right? So it's pretty easy to see. It is easy to see that the Cech complex of X and R is contained in the Vietoris-Rips complex of X and R, right? And so that should be pretty easy to tell. And one of the exercises that I'm going to have you do for next week, I think, or not next week, the week after, one like the problem set associated with this section is going to be for you to prove that the Vietoris-Rips complex of X and R is also contained in the Cech complex of X and R times root 2. Okay, so somehow these are almost equivalent. They're not quite exactly the same thing, but the Vietoris-Rips complex is just easier to work with. But they both give you a simplicial complex, and then you can, and there are actually a lot of different ways that you could imagine building a simplicial complex from data. So there are a bunch of other things, including things like alpha complexes, witness complexes. These are all in the textbook if you want to read more about them. So basically, there are a bunch of different ways of building these complexes. But once you have a simplicial complex, then you can ask things about homology. So what's the topology of this simplicial complex? And in order to do that, we need to give a couple more definitions in order to build up to understanding what homology means. So hopefully this isn't too boring for those of you who already know what homology is, but let's define it in terms of simplicial complexes. So let K be a simplicial complex, as you might get out of a Cech complex or via a Vietoris-Rips complex. Then an I chain is a formal sum of I simplices, sigma of Ci, sigma I, where our Ci's are in some field. And for our purposes, we're going to let the field be the field of two elements. Okay, so just the simplest possible non-trivial field. And the sum is taken over all possible I simplices, well, I simplices sigma I in K. Yep.
Just a good question. So in a VR complex, so you won't know if like all of them mutually intersect, right? Or you won't necessarily know that.
You won't necessarily know that, but you'll just even if all of them don't mutually intersect, you'll say that the simplex is present if you have all the edges that correspond to it.
Okay, so you still like fill it in.
Yeah, you'd still fill it in.
I see.
Yeah, and that's just easier to compute because if you want to actually check if all these balls intersect, well, that's harder, right? Because then you have to actually check all these things. But it turns out that if you have, say, 10 balls and all of them have pairwise intersections, well, I mean, you can sort of say, well, maybe then all 10 of them should intersect. They don't, but like often they do, and that's good, close enough for many purposes. And it turns out that these inequalities that we'll have you prove basically say that, I mean, it's sort of equivalent up to a rescaling of the distance of R. Like it's not actually equivalent, but it's close enough. But yeah, so here we have a formal sum, which just means that we're adding them together, but they don't mean anything. We'll think of this as a vector space in a little bit. And the set of all I chains is denoted Ci of K. And now if this were a more general algebraic topology class, you wouldn't just be working in the finite field of order 2. But for our purposes and for many practical purposes, we are just going to work in the finite field of order 2. So with 0 and 1 as elements. So for everything we do, that will be the case. So note that Ci of K is a vector space. Vector space over F called the vector space of vector space of I chains in K. Okay, and note that we do have a basis for this vector space. What's our basis? Yeah, just the simplices. So note that the I simplices form a basis of Cik. So the dimension of this vector space is just equal to the number of I simplices. Let's give a concrete example since we're going to go into abstract land. So let's say, my drawing goes across 2 pages. That's always a little bit irritating. Let's see. Okay, so let's say that we have this simplicial complex, which I'm going to label A, B, C, D, E for all our 0 simplexes. Let's label this A, B, C, D, E, F for all our 1 simplexes. And let's go ahead and label this, we have 1, 2 simplex here, this triangle. Okay. So then obviously, this is pretty easy to show. We have our 0 simplices, which are just the set A, B, C, D, E. We have our 1 simplices, which is going to be a set capital A, B, C, D, E, F. And we also have a 2 simplex, which is just going to be tau. Okay, so what are these vector spaces? Well, the vector space C0 of K is going to be the vector space generated by the elements A, B, C, D, E. So for example, maybe something like A plus C plus E. Okay, and for C1 of K, that's going to be the vector space generated by all the edges, summed together, C, D, E, F. And so maybe you have something like A plus B plus D plus E. Okay, and C2 is going to be pretty boring because that's just the vector space generated by a single element. And of course, since we're working over the field of order 2, that means that the only elements in this are 0 and tau. So, yep.
Does restricting ourselves to like the 2 element field just mean something is either present or not present?
Yes. Yep. And that will be key to many of the proofs that we'll be doing. So basically, this makes it really easy because you can identify points in the vector space by just saying, is this basis element present or not? Obviously, when you're doing a formal sum in some other field, then things get a little bit more complicated. So I-chains cannot just be identified with whether something's present or not. But since we're restricting ourselves to the field of order 2, like this all like works out nicely. It also becomes a lot easier to compute with because you can basically think of operations on these vector spaces as XOR operations on a big vector. Okay, so now we've defined these things. So now let's go ahead and define the boundary operator. Define the boundary of a simplex. Boundary of a simplex. And this will be quite important. So if we let sigma be equal to U0, U1 through UK be a K-simplex, then the boundary is just going to be all the faces of it. You're going to get all the faces from a simplex by taking the boundary operator. So the boundary of sigma is a map. Let's call it dk, or delta k, dk, whatever. That goes from ck of k. Oh, sorry, I've used k for both things. Capital K to ck minus 1 of capital K. And what is it? So the k of sigma is going to be equal to the sum from I equals 0 to k of U0, U1, Ui hat. I'm going to use Ui hat to mean that it's not present. Uk, where Ui hat means Ui is omitted. Okay, so that just means that this is some sum of all the k minus 1 dimensional faces. And let's give a concrete example of that. So if we go back to our favorite simplex here, let's see, A, B, C, D, E, A, B, C, D, E, F, and let's say tau is over in here. Well, then the boundary of tau, what's the boundary of tau? Yep. And what's the boundary of A? Yeah, so A plus B. So basically, the boundary operator lets you go from something higher dimensional and it goes down to something lower dimensional. And of course, since this is defined in all simplexes, this also then becomes defined on sums of simplexes. And so this is an operation that's defined on I-chains in general.
So I guess we're putting like the minus, one of the I factor because minus 1 is like the same as 1 in this field.
Oh, yeah, yes. So yes, that's the other reason why we've done this, is because minus 1 is equal to 1, which makes life so much easier. Yeah. Yeah, so you don't have to worry as much about things like orientation because minus 1 is equal to 1. Okay. So this is a simple, like I said, if you take an algebraic topology, this is a simplification of many things because for convenience and because when you're actually computing things, like those things get complicated quite fast. Okay, that's why I said like this is only true if you're working in the field of order 2. These definitions get a little bit thornier when you're working in other fields. Okay, and well, you can define a chain complex, and this is just going to be a sequence of chain groups. So a chain complex is just a sequence of chain groups. Groups connected by boundary maps. By boundary maps. So we have the I plus 2, which is going to go to Ci plus 1 of k. And that's going to go to the I plus 1 via the I plus 1 to Ci of k, and so on. Okay, so it's just some sequence of boundary operators. And for example, so this is going to go via the empty set to via D3 to tau, which is going to go via D2 to the space generated by all of our edges, which is If you're working in other, oh, there is a chat. Oh, sorry, let me pull up this chat. Yeah, yes, yeah. Ilya also mentions if you're working in other fields in general, there's a -1 to the n in front of all the terms. But we're working in the F2, so this is irrelevant. Yeah. But yeah, so we're doing a number of simplifications just to make life a little bit easier. A, B, C, D, E, which goes via D0 to the empty set. Okay, so that would be the chain complex for the particular example we had earlier. And we can also define something. Once we have these things, we can define a number of other terms. So let's define an Icycle, which is going, oh, I should actually define it first. So an I chain, C is an Icycle if di of C is equal to 0. Okay, so as an example, if you take d of C plus B plus F in our example up here, so C plus B plus F, that is equal to E plus D plus D plus B plus B plus C, which is equal to 2D plus 2E plus 2B, which is equal to 0, which implies that C plus B plus F is an Icycle. Okay, and so this is somehow formalizing the notion of like, well, cycles and things like that. And we're doing it by saying that the boundary of an Icycle is just going to be 0. And we can also define an I boundary. So this is definition 4.5. So what's an I boundary? So an I chain is an I boundary if it's the boundary of something that's if it's the boundary of an I plus 1 chain. It's an I boundary if there exists an let's give this a name. A boundary C, an I chain C is an I boundary if there exists an I plus 1 chain D in C I plus 1 of K such that C is equal to the boundary of D. Okay, and so our example is just going to be that B plus C plus F is an I boundary because it's the boundary of tau. And that brings us to the fundamental lemma of homology, which is lemma 4.1. It's going to be the fundamental lemma of homology, which is to say that if you take the boundary operator and compose it with the next boundary operator of the lower dimension, then that's always going to be equal to 0. So dp of dp plus 1 of d is going to be equal to 0 for all p in the integers and for all I chains. D. And this proof is really quite straightforward. So let me go ahead and sketch it out. So we need only show this for a p plus 1 simplex, because that would be a basis. Simplex tau. So that is to say, we need to show that dp of dp plus 1 of tau is equal to 0. Then the boundary, dp plus 1 of tau, consists of all the p faces of tau, right? Since it's a p plus 1 simplex, and so you have all the faces. You can think of a tetrahedron and all the triangular faces off of it. And you'll note that every p minus 1 face of tau belongs to exactly 2 p faces. Exactly 2 p faces. So we know that dp plus 1 of tau is equal to 0. Okay, and there is some analog for this in other fields, but we're really not going to worry about any other fields in this class. Okay, so now that we've defined all of these things, well, we can start thinking about what this actually means. And this allows us to actually define the homology groups. So now we have these facts. So let's draw this out a little bit. So let's go ahead and give, I will not actually have notation to, I think I'm about to run out of time. But let me just go ahead and write a couple more things down while we're still here. So in terms of notation. So let's let ZP be equal to, ZP be ZP of K, which is the set of P cycles, such that dP of C is equal to 0, which is also the kernel of dP, the subgroup of P cycles. And we're going to let BP be the subgroup of P boundaries. So this is going to be, and note that this is the image of BP plus 1. So this is the subgroup of P boundaries. And so one thing that we're going to define, actually, I think I have time to write down the definition. I think I'll end there. So definition, the Pth homology group, is the Pth cycle group modulo the Pth boundary group. So HP is equal to ZP modulo BP. And the Pth Betti number, is the rank of this group. So the Pth Betti number is equal to the rank of HP as a group. Okay, and I think I will end there. Well, we'll go over this again next time. So for those of you who have already know algebraic topology well, I apologize. This is going to be pretty boring. For those of you who don't, we will be taking a little bit of time and explaining this in a little bit more detail and reviewing this all. So that will be tomorrow's lecture. And yeah, thank you all very much. And I will see you guys tomorrow.